Hello, good morning. This is Professor S.K. Sahu from NIT Raulkela, India. The topic of my presentation is experimental and numerical studies on free vibration of laminated composite shallow cells in hygrothermal environment. Laminated composite cells are increasingly used in many engineering applications, including fuselage panels of airplane, especially Boeing 787, Airbus, turbine blades, automobile body panels, deep submersible vehicles, storage tanks, roofs of auditoriums and airport buildings and other structural elements due to lightweight, high specific strength and stiffness, excellent thermal characteristics, and ease of fabrication. These are some of the applications of composite cells. This is a part of a aeroplane. This is a ship. The research significance of this study: cell structures are often subjected to dynamic loads, and free vibration of composite cell structures is an essential component of its dynamic behavior. Many aircraft failures are attributed to dynamic behavior of composite panels. The vibration behavior of composite cells are significantly affected by the varying environmental conditions due to wide ranges of temperature and moisture absorption. Aircraft on ground and in air is having a very different temperature range, so also different temperature from cold to hot countries, boats and ships in seas. Therefore, the vibration of laminated composite panels subjected to hygrothermal loading are of great practical significance in the prediction of structural behavior of this type of structures. Coming to the literature review, some studies are available on vibration of cells subjected to hygrothermal load, though there are plenty of studies available vibration of cells in ambient temperature. Very few studies are available on cells subjected to hygrothermal load. Giving us some of the example are Padhi et al., Naidu Sinha, Nanda Pradyumna. They have studied hygrothermal effects on dynamic behavior of multiple plates and cells using finite element method. Mahapatra et al. Has also studied nonlinear free vibration of laminated cells with hygrothermal environments using FEM. Bises et al. Has studied free vibration analysis of smart laminated CNT reinforced composite cylindrical cells under hygrothermal conditions. However, these studies are numerical only. The experimentation on cell subjected to hygrothermal load are not available in literature. However, some studies are available on plates subjected to hygrothermal loading. Rath and Sahu has studied the dynamic behavior of plates subjected to dynamic hygrothermal loading. Even there is another study, Panda et al. Has studied also hygrothermal behavior of cells subjected to hygrothermal temperature and moisture. Coming to the critical discussion, many researchers have worked on vibration analysis of laminated composite cells in ambient temperature and moisture conditions using various analytical and numerical approaches. The numerical studies on free vibration of unidirectional laminated composite cells subjected to hygrothermal environment are limited in literature. The experimental studies on laminated composite cell vibrations under hygrothermal environment showing practical insight to the actual behavior are not reported in literature, and thus becoming the subject of the study. Based on the Lilbrook literature, the problems identified for the present study are vibration of woven fiber glass epoxy laminated composite cell panels in hydrothermal environment is studied by both experimentally and numerically using finite element method. The effects of curvature ratios, number of layers of laminate and lamination sequences on natural frequencies of laminated composite cells for different temperature and moisture concentration under different boundary conditions. Coming to the mathematical formulation, this was a typical doubly curved shell element. The analysis is, there are some of the assumptions. The analysis is linear. This implies both linear conjugative relations and small displacement. The curved panels doesn't have any imperfection. All damping effects are neglected. This is the equation of motion of doubly curved laminated composite cells subjected to in-plane loads under hydrothermal environment. So there are the terms related to NN, NXN, NYN, NXYN are the terms coming due to the hydrothermal environment. This is the non-mechanical forces entering into the equation of motion due to hydrothermal environment. Coming to the finite element formulation, an 8-noded doubly curved isoparametric element based on first-order shear deformation theory is used for the present analysis of woven fiber composite cell panels subjected to hydrothermal loading. At each node, 5 degrees of freedom U, V, W, theta x, theta y are considered. This is the element. This is the strain displacement relation with curvatures in x direction, y direction, and twisting curvature as well. Shear deformation has been considered. This is the nonlinear strain components used to derive geometric stiffness matrix due to the mechanical and non-mechanical loads. As you can see, there is a force component Fn. So F are the normal forces Nx, Ny, Nxy, Mx, My, and Mxy, Qx, Qi. So these are the components normally we experience in a composite forces. These are the first three are the in-plane forces. Next three are the bending forces. The Qx terms are the shear forces. This covers to d epsilon. D is the constitutive relation, and Fn is the force developed due to hydrothermal condition. This components comes into picture when any structure is subjected to hydrothermal condition. This is reflected in the F equation as well. So this is the constitutive relation D, which can be derived with respect to the stiffness coefficients, the in-plane coefficients, the bending coefficients, and the shear coefficients are found out like this. And a shear correction factor of 5/6 is considered throughout the analysis. In this slide, beta 1, beta 2 are the moisture coefficients of the lamina. Alpha 1, alpha 2 are the thermal coefficients dealing with the temperature of the specimen. C0 and T0 are the reference moisture percentage temperature in Kelvin. The element residual stress stiffness matrix due to hydrothermal loading is expressed in line with Cook et al. For mechanical loading, and this is G transpose S G Jacobian, modulus of Jacobian, d xi d eta. This is the extra stiffness coming in for the composite formulation. Solution procedure. The stiffness matrix, the initial stress stiffness matrix, the mass matrix, and the load vector of the element are evaluated by performing the numerical integration by Gaussian quadrature. The element matrices are assembled to obtain the respective global matrices. Stiffness matrix K, this is the bending stiffness. The initial stress stiffness matrix due to hydrothermal, K sigma R. or K sigma n, and mass matrix M. The equation for free vibration of cell panel subjected to hydrothermal loads may be expressed as K plus K sigma R. This is the extra terms coming for hydrothermal loading minus omega square mq is equal to 0. This becomes an eigenvalue problem. So a eigenvalue solver takes care of this and gives us the frequency in radian, which again can be converted into hertz, frequency in hertz. A program is developed in MATLAB environment to compute the natural frequencies of the cell subjected to hydrothermal environment. Coming to the experimental program, the materials used is woven fabric glass epoxy fiber, e-glass oven rubbing as reinforcement, epoxy as resin, hardener as catalyst, 8% of the weight of the epoxy, polyvinyl alcohol as the releasing agent, and the fabrication has been done with the hand layup method. Liquid resin is placed along with reinforcement, the open glass fiber against finished surface of an open mold. The percentage of fiber and matrix taken are 50:50 by weight. Geometry of the specimen, size of the plate and cylindrical cell panels is 0.21 meter into 0.21 meter. Thickness of the plate and cells 0.003 meter, 0.0045 meter, and 0.006 meter for 8 layer, 12 layer, and 16 layer woven fabric glass epoxy specimens respectively. The density of the specimens are 1690 kg per meter cube. The radius of curvature of the cylindrical cell panels have been found out 0.867 meter, 1.154 meter, and 2.09 meter. This is how the fabrication has been carried out. The specimens are treated in a oven for increase in temperature. The specimens are treated to moisture in a humidity chamber. Then the material elastic constants were determined experimental in Instron 8862 for different temperature and moisture concentration by tensile test as described in ASTM standard D3039. Free vibration test has been conducted with FFT analyzer Burel and Kager 3560C. For this, a modal hammer BNK 23025, accelerometer BNK 4507 has been used. A Pulse Lab software has been used at the interface. The boundary conditions for the free vibration test: 4 sides simply supported, 4 sides clamped, 1 side clamped and 3 sides free, that is cantilever, 2 opposite sides clamped and 2 other sides free. These are the boundary conditions considered. So this is fully clamped cell specimen subjected to hydrothermal loading. This is the cylindrical cell specimen subjected to simply supported boundary conditions subjected to hydrothermal loading. This is the cantilever specimen. This is a typical FRF showing the frequency response spectrum and the corresponding coherence curve showing the accuracy of the measurement. The result and discussion. The first one is convergence study. A convergence study is carried out to find out the fundamental natural frequency of 4-side simply supported cylindrical cells under hydrothermal field for different mesh size like 4x4, 6x6, 8x8, and 10x10. As shown is the table. The mesh of 10x10 shows good convergence and is used throughout the study. Comparison of non-dimensional frequency of simply supported laminated spherical cell for different temperature and moisture conditions to validate the formulation. So we have found out the present finite element. These are the present finite element results are compared with the Nanda and Pradyumna and Naidu and Sinha available in literature. They have used also the finite element. So the finite element formulation, present finite element formulation is validated with their formulation as well. The elastic moduli of the material found during tensile testing E1 15.94, which gradually decreases to 14.12 with the application of temperature. Similarly, the shear moduli is 3.57 and gradually reducing to 3.49 by increasing the temperature from 300 to 375. Similarly, the effect of elastic moduli due to moisture concentration, the elastic moduli Young's modulus E1 is 15.94, reducing to 14.8 with the increase of moisture from 0 to 0.75%. Similarly, the shear moduli decreases from 3.57 to 3.39 with increase of moisture. Coming to numerical and experimental result. So this is a simply separated cylindrical cell panel. Different R by B ratio has been shown. The last one is the R by B infinity, means actually a plate. These are all cells. The frequency is increasing with the increase of curvature of the R by B of the panels and decreases with the increase of temperature. All the frequencies are decreased with the increase in temperature. The temperature has been increased from 300 to 375 degree. So at 300 Kelvin, the fundamental frequency is increased in the range of 15.87%, 45.64%, and 72.58% as compared to that of a plate by providing a curvature ratio of 9.95, 5.949, and 4.13 respectively due to increase of stiffness. The fundamental natural frequency reduces by 40.97% and 57.05% with the increase of temperature. Similar studies have been carried out with clamped boundary condition. The frequency also reduces, though the clamped frequencies are significantly higher in comparison to the simply separated cell panels. The frequency is reduced with the increase of temperature. Similarly, for cantilever cell panels, cylindrical cell panels, the frequencies are much less in comparison to the other simply separated and clamped cell panels, and the frequencies reduce with increase of temperature, though of different percentage. Similarly, studies are also conducted by moisture concentration. The moisture is varying from 0 to 0.75%. The cells are, as you can see, that cell panels are affecting significantly with the increase of moisture at 0.5 moisture concentration. So the plate and the shallow cells are coming to nearly negligible stiffness. Similarly, at 0.75, the cell panels are coming to negligible stiffness. In comparison to temperature, the cell panels are significantly affected with the moisture. Similarly, the effect of moisture on the clamped boundary condition, the frequency is reduced with the increase of moisture. Effect of radius of curvature and frequency of angle plate composite cell panels in agrothermal environment. So studies are also conducted, though this is a woven fiber. We have oriented the woven fiber in the direction of 45 degree and minus 45 degree. So, and fabricate the specimen and tested it. As you can see that this was a slightly different configuration, and the frequencies also reduced with the increase of temperature. The effect of curvature and frequency of angle plate composite cell panels for clamped boundary condition, though the frequencies are significantly higher, but it is reducing with increase of temperature. Next is the effect of number of layers. The study is also undertaken for different number of layers. So there is a 8-layer specimen, there is a 12-layer specimen, there is a 16-layer specimen. With increase in number of layers, the frequencies increase, and the 8-layer specimen is reaching to negligible stiffness at 350 degrees specimen, but the 16-layer specimen is still having sufficient stiffness at 375 degree temperature. This happens due to the effect of bending, stretching, coupling. Similarly, the effect of number of layers is studied also for the moisture concentration. With increase of moisture, the cells frequency has been found out for different. So at 0.5 frequency, 0.5 moisture concentration, one is for 0.5, 8-layer is negligible stiffness at 0.5 moisture concentration, but the 16-layer shows a very high stiffness, and significant stiffness is still retained, though everything is decreasing, is retained with increase in number of layers. So some numerical studies only are found out for doubly curved cell panels under hygrothermal loading. So this is a spherical cell panel subjected to fully clamped boundary condition for different curvatures. So the frequencies are significantly increasing with respect to the cylindrical panels, but they decrease with increase of temperature. The effect of moisture concentration on the frequency of spherical cell panels subjected to clamped boundary conditions. So if the frequencies decrease with increase of moisture concentrations. Next, doubly curved hyperbolic paraboloid panels under hygrothermal loading. This behaves, the frequencies are more or less looks to the plate frequency, though it is a cell, and the frequencies decrease with increase of temperature. This is the effect of moisture on the natural frequency of hyperbolic parabolic cell panels in fully clamped boundary condition. The frequencies decrease with the increase of moisture concentration, but tends to have less reduction within as compared to spherical and cylindrical cell panels. Coming to the conclusion, the fundamental natural frequency of free vibration of laminated composite cell panel increases with decreasing the curvature ratios in all boundary conditions, with maximum increase for the simply separated case. With increasing the number of layers of laminates, the fundamental natural frequencies of laminated composite cells increase. The natural frequency of free vibration of laminated composite cells is reduced with the increase in uniform temperature and moisture concentration due to reduction of the stiffness. The fundamental natural frequency of cylindrical cell panels in hygrothermal environment are reduced more, followed by spherical and hyperbolic paraboloid cell panels. In all the cases, the experimental results match well with the numerical predictions. A generalized finite element based formulation is developed for the vibration of cell structures subjected to temperature and moisture conditions. A program is developed in MATLAB environment to compute the natural frequency of vibration using present formulation. The benchmark experimental and numerical vibration results presented in this investigation can be suggested as design aids for cell panels subjected to hygrothermal loading for the range of geometry and material parameters. It can be concluded that the free vibration behavior of cell structures are greatly influenced by the geometry, material, boundary conditions, and hygrothermal conditions. These experimental results can be a benchmark problem to many researchers and helpful for design of composite cell. The pre-evaluation results can be used as a technique for structural health monitoring or testing of structural integrity, performance, and safety. The above recommendations for design of composite panels are valid within the range of materials, hygrothermal, and geometrical parameters utilized in the study. These are some of the references used in this study. These are the publications out of this study. One is in composite structures, other one is composites part B. Both are also there. Thank you for your patient hearing.